Hi, my name is Martin Hjelm. I'm here to talk about sparse summarization of robotic grasping data. I'm from the Royal Institute of Technology, the Center for Autonomous System COS, the Computer Vision and Active Perception Lab QAP. To summarize, our main contribution is a method for doing simultaneous dimensionality reduction and clustering. We have evaluated this in a grasp transfer scenario. By a grasp transfer scenario, we mean transferring grasp knowledge to grasp novel objects. The idea is that the knowledge about the shape of the parts of the object that are used for grasping should be transferable when grasping novel objects. In the training phase, we teach grasps to the robot, and then we segment parts around the grasping points. We then use that for summarizing similar grasp shape segments. And by summarizing, we get a dictionary of prototypical grasps. These prototypical grasps contain our knowledge about grasping the different types of shape segments. And we use these prototypes to infer how to grasp new objects that we have yet not observed by comparing the new shape segments that we record to the prototypes. So, to summarize, the problem we were looking at was, given the gripper and the point cloud data, how can we summarize the knowledge contained in the data such that we can make generalization and transfer that knowledge. So in the image we can see an evaluation using a method. Green dots here that corresponds to cylindrical shaped prototypes, red dots corresponding to a cuboid shaped prototype, and the blue dots that corresponds to a shape in between a box and a cylinder. The problems with our data are the general problems you face with a data-driven approach to grasping. The data is high-dimensional. We have the grip parameters. We have a point cloud. It's continuous. And to clarify this point, how can we summarize this data into discrete prototypes? There's scarcity. This data set was quite small, since collecting grasping data and robotic data in general is very time-consuming. So, the summarization is essentially a high-dimensional discretization problem. Discretization is similar to clustering, and it's expensive to cluster in high dimensions. Therefore, to be able to discretize, we also need to reduce the dimensions of the data to afford the clustering. Further on, there's usually a lot of redundancy in the structure of the high-dimensional data, and not all dimensions are informative. The general procedures for solving these types of problems, like clustering and dimensionality reductions on these types of data, are usually quite blunt in the sense that they involve combinations of methods that need to be tuned to each other's. And these are the problems we want to alleviate with our method. Now, how does our method work? How do we summarize our measured data in a lower dimensional space? Well, it's illustrative to think about the problem from the other direction. So what if we already had this perfectly clustered representation in a lower dimensional space, and that each cluster could be represented by a point that explains the points belonging to that cluster. The cluster points here are the colored circles, and we can denote them by X. You can think about them as a lower dimensional representation of the shaped parts. The cluster centers that explain the points in the clusters are the red stars. We denote them as U. The U here is a summarization of all the shapes in that cluster, basically our prototypical grasps. Now we can also imagine that each cluster point corresponds to some point in a high-dimensional space. And this is our measured data Y, the gripper and the point cloud variables, and so on. And how can we map to the points in the high-dimensional space? Well, we could use Gaussian process regression. Gaussian process regression is flexible, it's non-parametric, and it's practical to work with. It's very easy to implement and so on. So it has a lot of good things that come with it. In a Gaussian process regression, we put a prior over the function space. So we can write the joint probability over the y's and the functions f and decompose it in such a way that we get a prior over f, as we see here. Now, if we add our cluster centers to the joint probability, together with our belief about the clusters, we get the following joint probability. This joint probability decomposes in the same way. However, f is now conditioned on the function values of the cluster centers, the FUs. This follows from the explanatory power of the cluster centers, meaning that we can remove cluster points but still retain the same GP, approximately. Now, it turns out that this formulation is mathematically equivalent to sparse Gaussian processes, so we can use that full arsenal for our mapping. Now, if you remember, all we had was our measured data y, and we wanted to find a lower dimensional clustered representation of that data together with this mapping done by GP. So if we assume that our data is generated by some not yet seen latent variable x, and we put a GP prior on the mapping of the latent variables, we get a Gaussian process latent variable model. And the GP-LVM looks like this. The probability of y given some latent variable x that generated y. The dimensions of y is considered independent given x. And we learn the latent representation by optimizing the posterior. Now, if we add our cluster centers and parameters of the GP to the mix, we get the sparse GP-LVM version. The posterior is proportional to the following expression. And here I've baked in the x variable and the parameters for everything except those that affect u's to make it more readable and to put a bit of focus on our major contribution, which is this. We have coupled the parameters theta u between the GP prior on FU, cluster centers, and the prior on the cluster centers. And what this means is that the mapping and the representation of the cluster centers are interdependent. And I will get back to this coupling in a minute, but first let's summarize where we are quickly. So by taking this backward route, we have arrived at the same solution as the sparse GP-LVM. We have a latent representation of the measurements. We have a cluster center representation with this power to describe the cluster points. And we have a mapping between the lower dimensional representation and the higher dimensional data. And we find these simultaneously. So we have to keep in mind now that the latent representation is not yet clustered, since we haven't put any prior belief on the points that are the cluster centers. That sort of encourages this clustering. So how do we do this? Well, our intuition about this said that if the points that represent the clusters are only representing points within the clusters, then the correlation between these cluster centers should be as uncorrelated as possible. So by encouraging the separation, we also encourage the clustering. And we therefore put a prior on the cluster centers U, and the latent space that encourages this separation. And the prior on a cluster centers U is a zero mean Gaussian of the function d. And we can see that a d value close to 0 will therefore be preferred. And the d function looks like this. K here is the covariance function between the ith and the jth centers. Theta specifies how strong that correlation is in terms of distance. The prior on U therefore states, if the covariance between the cluster centers are not summing to 0, then this representation should have low probability. So the GP-LVM is now encouraged to search for a solution with separated cluster centers. Now, all this is not quite enough. I talked before about the coupling, and what we did was to use the same covariance function with the same parameters in the GP prior of the cluster centers and the FU, as for the prior on U. So by coupling the GP prior and the latent prior, it sends a message to the GP-LVM that it has to take into account these cluster center constraints in the latent space when finding the latent representations. You can think about it as weighing two things. The most probable latent lower dimensional representation that had generated our data, y. So basically, if we remove all cluster points except the cluster centers, we should still have the same GP. And the other part is the best summarization of the data in the latent space. So now we have our method, and if we go back to our grasp summarization, the prototypes, we can take a look at how we specifically used our method to further the understanding of this data. So in the original work, there was different granularities, but they were difficult to achieve. And we wanted more prototypes to be able to match more shape segments, basically to be able to be more nimble. We had a hunch that the data could be divisible into 5 rather than 3 categories. So in our model, the number of cluster centers are set manually. So we ran our method just by saying, let's see what 5 clusters can do. And as we can see in the image, the added granularity allowed us to discern more sensible prototypes for grasping novel objects. So basically, we have more shape segments that we can match to new objects. And to summarize briefly what we have done in relation to previous work, we have a one-way pipeline for doing both dimensionality reduction and clustering. I will repeat that. We have a one-way pipeline for doing both dimensionality reduction and clustering. So despite all the math behind the method, we can just like plug in the data and run. Very simple. And there's a simplicity here in choosing the number of prototypical grasp or the cluster centers or whatever you want to do with this method. And since this is one process method, we can also iterate much quicker and understand the data much better. So instead of having to tune 1 or 2 methods to each other, and then you change one parameter in the other, or the clustering part or the dimensionality reduction part, you can just focus on analyzing the data. And we also have a generative model from the lower dimensional space. So let's say we have been ordered to form a gripper in a special way to prepare for a probable grasp. We can just generate this form in the high dimensional space. And we also have a probabilistic method for associating new data to prototypical grasps. So if you find a new data point, a new shape segment, we can match that to this prototypical grasps quite easily. And I think time's up, and see you in the future, basically. And if you have any questions, you can email me at mahj02@kdh.se. Or Martin Hjalm@kdh.se. Thank you.